Hello everyone, my name is Avkash. Welcome back to the second part of our All Things VQGAN series. In the first part of this All Things VQGAN series, we have covered AutoEncoder with extra emphasis on latent space and reconstruction error. If you haven't completed the tutorial, here is the link for you to complete it before jumping to the second part. In this second part, we are going to cover Variational AutoEncoder and VQ or the Vector Quantized Variational AutoEncoder with most emphasis on the codebook. So the variational autoencoder are the extension of the autoencoder. Before we try to understand the variational autoencoder, we have to understand two issues related to autoencoder. The first problem related to autoencoder is that the latent values in the latent space are not uniformly distributed based on input data similarity. Instead, they are scattered everywhere. Here you can see that we have a 512 by 512 image, and we are going to encode this image from 512 by 512 to 256 by 1 latent space through the encoder. And as you could see that, and these are the latent vector for the given source image. Similar to first image, we also have another image which is quite similar to the first one, and by using the encoder and encoding this image from 512 by 512 to 256 by 1 latent space, we generate these embeddings or these latent vectors. As you can see that these values are not uniform within a range. Instead, they have their own encoded range. And this is the first problem. The second problem is also related to the previous one because the latent vectors are not uniformly distributed. Because the latent vectors are not uniformly distributed, it causes the distribution to be not centered in the latent space. So the latent vector of the input data such as images are scattered everywhere and anywhere. So because of this, the input values are located at very distant locations even when they are quite similar to each other. In this given example, these two koalas are quite similar. However, in the latent space, they can be placed quite far even when they are quite similar. So we can summarize the two main problems with autoencoder. First, the latent values in the latent space are not uniformly distributed based on input data similarity. Instead, each one has its own distribution range. And the second, the latent vectors are located at very distant locations or they distributed across latent space even when they are quite similar to each other. And to solve these two problems, we have introduced the variational autoencoder. It means the variational autoencoders are introduced to solve the both of the key problems introduced by autoencoders. To solve both the problems, the variational autoencoder reparameterize the latent space by adding the mean and the standard deviation of the encoded values. It means along with the original latent values, the mean and the standard deviation are also added into the latent space. If you remember, the autoencoder example we have covered earlier, the first problem was that the values or the encoded latent values in the latent space for each input image had its own range. However, with introduction to the mean and the standard deviation into the latent space, the values are ranging between 0 and 1. This way, all latent vector values are uniformly distributed between the range of 0 and 1, as all the values in the latent space are having a uniform distribution of values to be between 0 and 1. Now, close or the similar images or the images with similar features can be placed next to each other in the latent vector space. So by applying mean and standard deviation, the encoded values are close to the origin, as all the encoded values in the latent space are using the similar scale. So let's summarize the variational autoencoder. First, it's an extension to the autoencoder. Second, it applies mean and the standard deviation to the latent vector values. It keeps all latent vector values to be within the range of 0 and 1. The similar latent vectors are placed close to each other depending on their latent vector values similarity. At this point, we have covered both autoencoder and the variational autoencoder. So the question comes, why there is a need to even choose the vector quantized variational autoencoder or VQ-VAE. Let's understand it next. Here is the research paper related to VQ-VAR or the vector quantized variational autoencoder. The research paper abstract explains that the VQ-VAE model, the vector quantized variational autoencoder, differs from variational autoencoder in two key ways. First, the encoder network outputs discrete rather than continuous codes. And the second, the prior is learned rather than static. It means the representation in the latent space is discrete, it's not continuous. So let's understand it. So to understand VQ-VAE, we must understand these two concepts. First, the discrete data representation, and the second, the prior is learned rather than static. First, let's try to understand the continuous data representation of the latent space in variational autoencoder. With autoencoder, all values in the latent space are taken from a continuous latent space and decoded for the target data or the input image based on continuous representation of the encoded data. So, due to this continuous representation of the data based on input data or images, there can be massive amount of data processing is required. However, you must know that lots of these images are going to have similar features. Changing from continuous to the discrete data representation in the latent space, we do not need to select all images. Instead, we just need to process some of the latent vectors. So adding the discrete representation of vector data in the latent space solves two big problems. There are less number of vectors in the latent space to process, and the second, because now we have discrete data and these values are scattered sparsely in the latent space. We have already understood how does variational autoencoder works and the advantage of adding mean and the standard deviation to the latent space. Now we can learn the vector quantization process in the same variational autoencoder. In a vector quantized variational autoencoder, we introduce the vector quantization between the encoder and the decoder as an updated latent space with the introduction of a codebook. So we can say that the vector quantization takes the advantage of vector quantization with the help of codebook. And codebook is a very important feature of vector quantization process in VQ-VAE or also while understanding the VQ-GAN. If you understood the concept of codebook in VQ with respect to autoencoder and the VQ-GAN, you will not only understand VQ-GAN, but also you will be able to understand how the text-to-image transformer works for very popular text-to-image projects such as Dall-e and the Dall-e 2 and the Glide, all from OpenAI, Imagen from Google, and the open source implementations of Dall-e such as Dall-e Mini and Mega, and also the Dall-e. And because the codebook is very important part of VQ-GAN, so I will try my best to explain you here with detailed explanations. To understand how the codebook is created, you first need to remember the continuous space. We have all encoded values for the all input images. Here with the discrete space, we do not need all the encoded vectors for all the images. Instead, we just set a smaller number of codebook size based on input images. So let's assume that we have 100,000 images. For 100,000 images, we can generate a codebook of size 8192 or the 1024 entries in the codebook. Each entry of the size 256 by 1 vector. This way, we do not need to process all 100% of the images. Selecting 1000 entries in the codebook against 100,000 source images means we are using 1% of original processing power to process 100% of the source data. So using discrete method by applying codebook, we are able to process massive amount of data with the smaller size of codebook. In practice, this method is quite complex, but for the simplicity, you can understand it by this way. So this helps us to prove the previous concepts of applying discrete data representation instead of continuous data representation by using vector quantization. So the million-dollar question is, how do we represent data into the discrete format while keeping the latent vectors count up to 1% through the codebook? So now let's take a look how the codebook is generated. Let's start that we have 100,000 source images and we are going to have 1024 entries in our codebook of the size 256 by 1 vector space. And we do have the encoder to encode input image of size 256 by 1 as defined in our codebook per entry size. Now let's process the very first image in our source. The first image is processed and its mean and standard deviation based encoded vectors are generated. At this point, all codebook entries are empty because this is the first entry. So the current encoded values is going to be placed into the codebook in its first place. Now let's assume the second image is going to be processed by the encoder and its mean and standard deviation based entries are added. Now the VQ or the vector quantization process will be active and the nearest neighbor entry will be checked from all the field entries inside the codebook. If any entry is found, the value inside the codebook will be replaced by the new entry. However, please remember that we are just creating the codebook. So let's assume the second entry does not find a nearest neighbor. So this value will be placed into the second position. Now let's assume the third image is going to be processed by the encoder and its mean and standard deviation based encodings are generated. Now the vector quantization or the VQ process works, and let's just assume that the entry at the first index in the codebook results as the nearest neighbor to the given entry. Then the entry in the codebook is replaced by the third image encoded value. So you must remember that both first and the third images have similar latent vectors. It means that both the images features are stored inside the codebook. So there is not significant feature loss. Yes, there is, but just a little. However, if the latent vector size is larger, then the loss will be minimal. This way, slowly, all the 100,000 images will be processed and all 1024 entries in the codebook will be updated based on the features from all 100,000 images. This is how your codebook will be created, which has all the features from the all source or the input images as encoded by the encoder. Now I believe that you have better understanding about how the codebook is created. However, there are a couple of things to add to make the VQ-VAE more versatile to extract features from the source data such as images. First, let's calculate that we have 100,000 source images and the codebook size is 1024 entries. And the encoder generates only latent vector per source images. So we just learn only 1024 features from our source images. In practice, the encoder actually generates way more features per image instead of just one. So let's understand how it helps us to learn more features from the source input images. Now, what if the encoder generates two latent vectors per source data or the image? It means the codebook will have two layers of total 1024 entries, each size of 256 by 1, and the variational encoder has to check entries from both the layers to update nearest neighbor and then update the table. With this change, there will be 100,000 images with 1024 size codebook with two latent vectors per image. It's going to give us 1024 to the power 2 features. Similar to it, if we have 16 layers of 1024 entries in the codebook, it is going to give us 10 to the power 24, 1024 to the power 16 features. As you could see, the growth in the codebook entries for each source data is going to give us more and more features. And now if we choose 32 features per image in our codebook, it gives us 1024 to the power 32 features. It means we have massive amount of features for the given input source data. And these features can be created by 100,000 images or by 1 million images or the 50,000 images. So the size of images will not matter. What matters is the features extracted from these images in the codebook. Having a very large size of features means more latent vectors per source data or the image. It means the codebook will be rich enough to have most of the features acquired from the source images, which will result into the better image generation during the decoding process. If you remember, we started our VQ-VAE topic with moving from continuous data representation to the discrete data representation in the latent space, and we promised that with the VQ-VAE we will be able to process the latent data discrete and sparsely. So with the introduction of Codebook, we can make sure that now the latent data is discrete and sparse both. To summarize the variational autoencoder, we can say that the Codebook keeps the n latent vectors per source. The value of n is defined by the problem and the autoencoder. Next, the latent vectors in the Codebook keeps the data representation discrete, and the statement prior is learned rather than static required a little more clarification. So let's look few more slides. So with the introduction to the VQ or the vector quantized, now I hope that you have very good understanding about the Codebook and how it is created. And you also know what is stored inside the Codebook. However, if we want to understand the VQGAN, we must understand that in practically why the Codebook is so powerful to generate the new images in VQGAN. So let's understand it next. If you give attention to the source image data, you will see that each image is a collection of several features such as sun, water, sky, sand, cloud, land, fence, bamboo, lake, tree, branches, road, ladybug, crop like a green leaf, hills, bricks, different colors of leaves and flowers, and so on. So based on given image in our example, as shown in this screen, we can store the features like sun, water, sky, sand, cloud, flower, land, fence, crop, leaf, hill, etc., etc., etc. So rest you can now understand that how each latent vector inside the Codebook holds a feature specific to the source data or the image. So virtually the Codebook is a collection of feature set from the source image stored and ready to be used by the decoder to generate images. So now the prior is learned rather than static can be understood as that the latent vectors stored into the Codebook are the learned features which are learned from the source data such as images. The content covered in this tutorial is also available at the All Things VQGAN folder at the DeepWorks repo in my CrowdRank GitHub account. All three parts of this VQGAN tutorial along with the resources and the videos are all available at this repo. So by the end of this second video in All Things VQGAN series, we have covered autoencoders, variational autoencoders, vector quantized autoencoders, and extra emphasis on latent space, reconstruction error, and the Codebook. It means we are ready to learn the VQGAN, where we are going to cover both VQ-VAE and GAN combined. So that's all I had for you in this tutorial. I hope you have enjoyed the content in my video. If you have liked it, please do share it. Please subscribe my channel and also comment your feedback or any suggestions you have. I do appreciate your time and I'm looking forward to see you in my next video. Until then, please be good and do good. Thank you.